Can you see it now?
Yeah. And please take it away.
Okay. I'd like to begin by thanking the organizers for giving me the opportunity to talk. So today I will be talking about an overview of the recent developments in the field of 5D SCFTs. So I will be focusing on two aspects primarily. So first one is the classification of 5D SCFTs, and the second is the study of generalized global symmetries. So these generalized global symmetries involve one-form symmetries, global form of zero-form symmetries, and some exotic symmetries, which are known as two-group symmetries, which are mixings between zero-form and one-form symmetries. And in both of these aspects, a huge role is played by a tool known as surface geometry, which we will discuss. So let's begin by reviewing some of the salient features of 5D SCFTs. So these theories are inherently strongly coupled. That is, they cannot be defined as Lagrangian theories, any weakly coupled Lagrangian theories. And usually their existence is inferred from string theory, M theory, F theory constructions. And many of the properties are studied using these constructions. These theories are related to 5-dimensional n equals to 1 non-abelian gauge series. And the relation is as follows. So you start from 5D SCFT and perform a mass deformation M. Now you obtain a 5-dimensional supersymmetric quantum field theory, which is not conformal. So this initiates an RG flow. And at the bottom of the RG flow, in many situations, you find that the low energy physics is described by this 5-dimensional supersymmetric non-abelian gauge theory. And one key point is that the mass parameter is encoded in the gauge coupling for this gauge theory, the inverse gauge coupling for this gauge theory. So as you tune the mass parameter to 0, you go back to the conformal theory, and this translates to the infinite coupling limit in terms of this gauge theory description. And this justifies the point that they are inherently strongly coupled theories. Okay. So now it's of one interesting point is that the flavor symmetry of the gauge theory is not equal to the flavor symmetry of the conformal theory in many cases. The symmetry can enhance when you go to the conformal point. And that these 5D SCFTs can carry two-group symmetries as well. This is what we will discuss later in the talk. And as I described earlier, two-group symmetries are mixings of one-form and zero-form symmetries. So let's review a well-known example of these 5D SCFTs. And the example we consider are known as ENF plus 1 theories or Seiberg theories. So we start by considering 8 5D SCFTs, which are parameterized by this number NF, and it goes between 0 and 7. All of these SCFTs have rank 1. This means that the conformal theory admits a Coulomb branch of vacuum, which has a real dimension of 1, equal to 1. So these theories are strong coupling limits of SU2 gauge theories in 5 dimension in the way I discussed on the previous slide. And the parameter NF becomes the number of fundamental hypermultiplets that the SU2 gauge group carries. Okay. So now there is an enhancement of the flavor symmetry at the conformal point. The gauge theory, as you can see, has an SO2NF part to the flavor symmetry, which rotates the NF fundamental hypers. And there is a U1 instanton flavor symmetry in 5 dimensions as well. So the gauge theory sees the flavor symmetry algebra SO2NF plus U1. And it's well known that it enhances to ENF plus 1 at the conformal point. So this flavor algebra is exceptional when NF is 5, 6, and 7. It is E6, E7, E8. And for other values of NF, this is the list of what we mean by ENF plus 1. And you can see that none of these is actually SO2NF plus U1. Actually, SO2NF plus U1 is a sub-algebra of all of these algebras. So there is an enhancement in all of these cases. Now, moreover, this even theory has the even theory out of all of this list of theories has a one-form generalized symmetry, which is Z2. And this can be easily understood. This can be understood as simply the center one-form symmetry of the SU2 gauge theory. And since we have a pure SU2 gauge theory, there are no fundamentals. The Z2 center for the SU2 survives as one-form symmetry. And this even theory, as we will discuss later, also has a two-group symmetry. This two-group symmetry mixes the Z2 one-form symmetry and the SU2 enhanced flavor symmetry. And one point to note is that this two-group symmetry is not visible from the gauge theory. This is unlike the one-form symmetry case where you could view it from the gauge theory. And the reason is that as you perform the mass deformation, the zero-form symmetry part SU2 is broken to U1I. And this breaks the mixing between zero-form and one-form symmetry. So the two-group symmetry is a property only of the conformal point. Okay. Now there's another interesting theory in this list of theories, which is if you take SU2 with 8 fundamental flavors. And this is well known that it is related to a 6-dimensional superconformal field theory. And the relation is as follows. The sixth theory is E-string theory, is known as E-string theory. And you compactify this theory on a circle of radius R. Then in the IR, this initiates an RG flow because now you have a mass scale. And in the IR, you find that the low energy physics is described by a 5-dimensional SU2 gauge theory with 8 fundamental hypers. The gauge coupling of this theory is now related to the radius. And now you see that the 60 limit is to take this radius to infinity, which is again an infinite coupling limit from the point of view of the gauge theory. So this gauge theory at NF equals to 8, its strong coupling limit is not 5D SCFT, but a 60 SCFT. And as we saw earlier, for lower values of NF, you got 5D SCFTs. So this is often said in the following way, that 5D SCFTs, which are strong coupling limits of SU2 gauge theories, descend by integrating out matter from a 60 SCFT, namely the E-string theory, when you compactify this theory on a circle. Okay. And now such a similar pattern is observed for many other classes of 5-dimensional gauge theories. For example, you can consider some gauge theories with some gauge group G. You have some hypermultiplets in some representation R of G and some number NR of them. And it's observed that if NR is below a critical value, CR, then we have a 5-dimensional SCFT in the strong coupling limit. While if NR hits the critical value, then we obtain a 6-dimensional superconformal field theory. So this leads one to the following interesting conjecture, that maybe all 5D SCFTs can actually be obtained by integrating out matter from 60 SCFTs on a circle.
Sorry, there is something slightly imprecise in the way you think about it. I think I've already complained about it in the past. It's not true that if you start from the non-abelian gauge theory and you go to strong coupling, you find the SCFT in 5 dimensions or in 6 dimensions. This statement is just not a true statement. The converse of that statement is true. Namely, if you start from the conformal field theory, it has a relevant deformation either in 5 dimension or in 6 dimension, and then you either compactify or turn on a relevant deformation, that takes you to the low energy theory. The way you phrased it is the strong coupling limit of the low energy theory. This is not a well-defined question. It's like asking what's the strong coupling limit of a theory of pions, and it's not true that the strong coupling limit of a theory of pions is QCD. This is just not a true statement.
Yes, so that's why I started from the point of view that you mentioned. So that is you start from conformal theory, and by doing this mass deformation in the IR, you find the gauge
No,
theory.
I didn't object when you said that, but I do object on this slide and on the previous one.
Yes, so I'm going to so that is the meaning that I have in mind. And when I say that the strong coupling limit is the conformal theory, it's just a phrase which is supposed to mean the former statement. That it's actually supposed to be viewed as a mass deformation. So it's just for convenience of language that I'm going to say that it's a strong coupling limit and should not be taken literally, as you pointed out. So thank you for that comment. Okay. So, so a similar pattern is observed for other kind of 5-dimensional gauge theories. So you can construct in string theory some 5D SCFTs, and you find that if you do a relevant deformation, you find these 5D gauge theories with some gauge group and some hypermultiplet. And if the number of hypermultiplets are less than a critical value, so it's less than a critical value for 5D SCFTs, while if you had constructed a 6-dimensional SCFT on circle, then you find a critical number of hypermultiplets. Okay. So this leads one to an interesting conjecture that maybe all 5D SCFTs can be obtained by integrating out matter from 60 SCFTs compactified on circle. Now here in this conjecture, the tricky part is to define integrating out matter. What does it mean? Because 60 SCFT is some inherently strongly coupled thing. You put it on a circle, you again get some strongly coupled thing. So what does it mean to talk about integrating out matter? Okay. Another point is that this is not even matter in all situations. So for example, there exists an RG flow from another rank 1,5D SCFT, which is known as even tilde. It's different from even, it's a cousin of even. And this is the strong, so I will use the words again, it's a strong coupling limit of SU2 gauge theory, pure SU2 gauge theory in 5 dimensions, where now it's not a vanilla SU2 gauge theory, but has a non-vanishing discrete theta angle pi. So starting from this even tilde 5D SCFT, we can obtain E0 theory, which is another 5D SCFT, by doing a similar kind of RG flow. But now you notice there was no matter to start with, so you're not integrating out matter. Instead, what you're integrating out is the BPS instanton particle of SU2. So this E0 theory also has no gauge theory description because you have integrated out this instanton. So there are these non-gauge theories as well, which lead to 5D SCFTs. And the question is, what does it mean to integrate out matter for this kind of generalized theories? So this example suggests an answer, and we can think of it as integrating out BPS particles that arise when you go on to the extended Coulomb branch of the 5D theory. So I will use this terminology throughout the talk, extended Coulomb branch. This is defined as follows. You look at the space of supersymmetric mass deformations of the 5D SCFT. And at every point in the space, you find some supersymmetric quantum field theory, which has a Coulomb branch. And you fiber the Coulomb branch on top of the space. So the combined total space that you obtain will be referred to as the extended Coulomb branch. So at a generic point on this extended Coulomb branch, the low energy theory is an abelian theory with some massive BPS particles in the spectrum. And we can try to integrate out these BPS particles. And now when you phrase it, the integrating out process in this way, it makes sense even for non-gauge theories like E0, because they have an Coulomb branch on which there is a notion of BPS particles. Okay, so now we want to implement this notion of integrating out BPS particles. And how do we do that? So this is the point where surface geometry, the tool of surface geometries comes into the picture, and it's very helpful to describe this process. So let's first define what a surface geometry is. We start from a collection of smooth, compact Kähler surfaces. These are complex surfaces, so four-dimensional, four real dimension. And we are imagining that they're embedded inside an ambient smooth Calabi-Yau threefold. So there is a map from this collection of Kähler surfaces into the Calabi-Yau threefold. And inside the Calabi-Yau threefold, these surfaces intersect with each other in some way. So the four cycles intersecting inside a six-dimensional space will generically intersect in a two-dimensional locus. So when you will restrict this intersection, the intersection locus onto each of the surface, you will find a curve living in each of these surfaces. And the embedding map is such that you're going to glue the two curves together when you embed it into the Calabi-Yau. Okay. Right. So the intersections of these surfaces are encoded in a data of gluings of holomorphic curves inside this collection of surfaces. And because you want to preserve Calabi-Yau condition, and there are various other geometric conditions, this leads to many consistency conditions for what this gluing data can be. And this is very constrained by these conditions. So finally, if you provide a collection of surfaces and some gluing data which satisfies these consistency conditions, that is what we will refer to as a surface geometry in this talk. This describes some relevant data about the Calabi-Yau threefold, which will be relevant for studying 5-dimensional and 6-dimensional theories in this talk. And the connection to this 5D 6D physics is made by compactifying M theory on this Calabi-Yau threefold that the surface geometry is describing. So M theory compactified on the surface geometry constructs the extended Coulomb branch of some putative 5D or 5D SCFT or a 6D SCFT compactified on circle. So now it should be noted that if I just write down a random collection of surfaces and gluing data, which is consistent, so some random surface geometry, it's not going to be either a 5D SCFT or 6D SCFT on circle. It won't have the right contractibility properties to give rise to a conformal point. And it's only very special kinds of surface geometries which give rise to 5D and 6D SCFTs. Okay. So now we want to integrate out BPS particles, and we will use surface geometries to do that. These BPS particles arise in this M theory, from M theory by wrapping M2 branes on the holomorphic curves inside the Calabi-Yau threefold. And there are, in principle, two ways of integrating out these BPS particles. You can either preserve the rank of the theory, or you can reduce the rank of the 5D theory. So rank here is the dimension of the Coulomb branch dimension of the Coulomb branch. And it's also equal to the number of surfaces, because each U1 gauge field, which gives a direction in the Coulomb branch, arises by compactifying the M theory three form on each surface. So these two ways geometrically correspond to whether or not in the process of integrating out a BPS particle, you're decompactifying a surface or not. Okay. So which one should we choose is the question. So in gauge theory, when we were integrating out matter, this always preserved rank because we were not touching the gauge algebra at all. We were just simply integrating out the hyper. So to start with, let's assume that we want to look at in ways of integrating out BPS particles that preserve the rank. And let's try to do some classification using this proposal. So these kind of integrating out of BPS particles which preserve the rank have a nice geometric interpretation.
I'm sorry for being so picky again, but what does it really mean to integrate out BPS particles as opposed to integrate out everything at a given momentum scale?
Yeah, you will integrate out other things at that
No, I'm just asking, what's the meaning of the phrase integrating out BPS particles?
So you have you're on the extended Coulomb branch, you have some mass parameters turned on, and you have some Coulomb branch parameters turned on. And then there are various BPS particles in the spectrum. Their masses are functions of these Coulomb branch and mass parameters. And now you want to tune these Coulomb branch parameters and mass parameters in such a way that a particular a BPS particle or some collection of BPS particles, their mass is tend to infinity, while some other BPS particles, their mass remains finite in this limit. So this typically corresponds to going to the infinity in the extended Coulomb branch.
But what does it mean to integrate out the BPS particles as opposed to integrating out everything or all the particles above a given mass or all the fluctuations above a given energy? What does this phrase mean?
Well, as I said, there can be there can be two BPS particles. One of them has mass higher than the second, and they are functions of these Coulomb branch parameters and mass parameters. And now you can try to change. You can try to move around in the space extended Coulomb branch, and then the second BPS particle at some point will go above the first BPS particle and go to infinity. I will carry with it some other states to infinity as well. While the first BPS particle, which was massive to start, which had higher mass, would remain.
No, I understand that there are various limits which some particles become very heavy.
Yeah.
And in that limit, you can integrate out the heavy particles, whether they're BPS or not.
Mm-hmm.
I just don't understand what it means to integrate out the BPS particles.
Maybe it's about I'm not being completely precise about the words integrating out. So I actually want to say that I'm taking a limit in this extended Coulomb branch.
Oh, so you're not integrating out anything?
No, I'm taking this limit, and people often say that you're integrating it out. Yeah. Just for convenience of language. Okay.
Okay, so you're just studying a limit of the Coulomb branch, not integrating out anything, BPS
Yes.
or not BPS.
Yes, I'm studying some infinite limits in the extended Coulomb branch.
That makes more sense.
Okay. Right. So this kind of integrating out processes, which preserve the rank of the 5D theory, have a very nice geometric description. They correspond to blowing down -1 curves inside the geometry, inside this collection of surfaces. So this is a very tractable problem and can be carried out explicitly. And now this leads us to the following proposal for the classification program. The first step is to find surface geometries when 60 SCFTs are compactified on a circle. So you can have two kinds of compactifications. First is a vanilla compactification where you just put it on a circle without doing something extra. And this is what we call as untwisted. And the second one is where you, along the circle, suppose your 60 SCFT has some discrete zero form symmetry, then you can turn on a background for this discrete zero form symmetry along the circle when you compactify it. And this is what we call as a twisted circle compactification of a 60 SCFT. So we want to first find out surface geometry for both of these kind of compactifications. And then the second step is then to start from the surface geometries, perform all possible sequences of blowdown operations. And this leads to some new surface geometries. And then you declare that, okay, these surface geometries are actually surface geometries corresponding to 5D SCFTs. And you can recover various data about it.
You only consider twisting by discrete symmetries, not continuous symmetries? Or?
If you twist by a continuous symmetry, that's just a mass parameter.
Mm-hmm.
Because it can be continuously connected to untwisted case. So it's just a single theory. You go onto the extended Coulomb branch of a single theory. But if you twist by a discrete symmetry, you cannot continuously connect it to identity, and it gives to another whole space of extended Coulomb branch. So another class of 5D SCFTs.
Okay.
Lakshya, I have a question. Can you say a bit more what the gluing conditions for these surface geometries are from a field theory point of view, or is that just not accessible?
No, they are. So there are these things called triple intersection numbers between the surfaces. You can have triple intersections between them, and these triple intersections encode the Chern-Simons, some Chern-Simons couplings in the gauge theory, in the abelian gauge theory arising on the extended Coulomb branch. And now these triple intersection numbers can be computed in various ways from the point of view of different surfaces. So point of view of the three different surfaces participating in the triple intersection. And all these three different ways, they should match to give the same triple intersection number. So field theoretically, you're computing a Chern-Simons term from three different points of views, and it should be the same Chern-Simons term.
So in the low energy of a 5D, for example, so these gluing conditions, they specify some topological sector for the theory. Is that what you're saying?
The triple intersection number is the Chern-Simons term, and there are the gluing consistency conditions are just different ways of computing the same number, so they should match.
Okay.
Okay, so let's discuss the first point in this classification program of finding surface geometries for 60 SCFTs compactified on a circle. So for this, we use the fact that 60 SCFTs can be constructed, or the ones that we know can be constructed by compactifying F theory on singular elliptically fibered Calabi-Yau-3 folds. And then there is a famous M theory F theory duality, which states that if you perform a circle compactification of this F theory background now without any twists, then you can equivalently describe the setup as M theory compactified on the same elliptically fibered Calabi-Yau-3 fold. Okay, so now what this means is that you take this elliptically fibered Calabi-Yau-3 fold, you take a 60 SCFT, you want to study what the surface geometry corresponding to its circle compactification is. So you simply blow up this elliptically fibered Calabi-Yau-3 fold, and this would give you the surface geometry. So this is for the untwisted case. And now from this, you can extract some general lessons about what happens when in 6 dimensions on the tensor branch, you had some gauge algebra and some tensor multiplets of that kind. You get this piece in the full surface geometry. And then when you go to the twisted cases, these pieces are just combined differently. So by extracting these general lessons, you can extend, people have conjectured surface geometry also for the twisted cases as well. So in this way, first starting from resolving the Calabi-Yau-3 folds, getting some general lessons from them, and extending it to twisted cases, this problem of finding surface geometries for 60 SCFTs, circle compactifications of 60 SCFTs can be solved. And now the next step is to perform blowdowns. So this has been explicitly performed up to rank 3. As you go higher in rank, it becomes more complicated because there are more and more theories to consider. But you can put it on a computer probably, and that can do the job for much higher rank. But from this new point of view of 6 dimension, if you revisit the classification of rank 1 5D SCFTs, you find a surprise. You find the discovery of a new rank 1 5D SCFT, which we call as E0 adjoint, which was not known in the previous literature. So previously, we knew about these ENF plus 1, rank 1 5D SCFTs, and the E1 tilde theory that we discussed earlier. But now there is this new E0 adjoint theory, which can be constructed in a similar way as E0 was constructed from E1 tilde that we discussed earlier, where we integrated out the BPS instanton. So now, instead of starting from E1 tilde, which corresponded to the 5D gauge theory SC2 with discrete theta angle pi, we now start from this 5 degree theory SU2 with discrete theta angle pi, and we add an adjoint hyper to it. So this 5 degree theory lifts to not a 5D SCFT, but a twisted circle compactification of 6D A2 n equals to 2, 0 SCFT. And now if we integrate out adjoint from it, we go to even tilde. But now we can also integrate out the BPS instanton, just like we integrated out in even to go from even tilde to E0. And if we integrate out the BPS instanton without integrating out adjoint, we obtain this new theory E0 adjoint. So this is a simple way of understanding why this theory E0 adjoint should exist. And its M theory construction has some points which are different from other cases. So we believe that there is some non-geometric ingredient involved in the M theory construction, whose identity is so far unknown. And we know that this ingredient should exist because there is a particular holomorphic curve in the surface geometry that an M2 brane is not allowed to wrap. This is just for consistency purposes. And this is not a geometric effect. It should be due to some flux of some field in the M theory. And it would be interesting to figure out what precisely this non-geometric ingredient is. Okay. So now we have this classification proposal, which can be explicitly carried out. The question is, does it satisfy some checks? What are the checks that we can perform? Yes.
May I ask a question on the previous slide? So when you say that the M2 brane cannot wrap this curve, do you mean while preserving supersymmetry or at all?
At least while preserving supersymmetry. I don't know if at all, but there should not be a BPS particle corresponding to it.
Okay, thank you.
Okay, so the question is how to check this classification proposal. And for this, we turn to another way of constructing 5D superconformal field theories using surface geometries. Okay, so in this way, what we do is we just pick some surfaces and some consistent gluing data so that we have a consistent surface geometry. And then our task is to find a Kähler form, which can be written in terms of only the compact surfaces inside the Calabi-Yau threefold. No non-compact surfaces are allowed. And this Kähler form should have the property that all the curves and surfaces in the surface geometry have positive volume under this Kähler form. And if you can ensure that it has been argued in this paper, then this means that all the curves and surfaces can be contracted to zero size simultaneously. And if that can be done, that means that is the conformal point. So the original surface geometry you started with described the extended Coulomb branch of some 5D SCFT. Okay, the second input that we need is a correspondence between surface geometries and 5D gauge theories. So given the data about a 5D gauge theory, a supersymmetric gauge theory, namely a gauge group, some hypermultiplets, Chern-Simons levels, discrete theta angles, and what are the half hypers versus the full hypers, you can write down a canonical surface geometry for each such gauge theory. Okay, so now we take this gauge theory, F4 with three hypers in 26-dimensional irreducible representation. And using this rule, we write down the surface geometry for it. And then we check that whether we can find a Kähler form which satisfies this condition. And it's known that it is satisfied. There exists such a Kähler form. So this means that we have constructed a 5D SCFT. But it can also be shown that this surface geometry for F4 with 3 flavors does not arise in the previous classification that we have been considering. So various SU, SO, SP case theories are in the classification, but only for some exceptional groups like F4, E6, and E7, some handful of cases do not arise in this classification. So the classification is not complete. Okay. Now, does it mean that it cannot be constructed at all from 6 dimensions? That's not true. So it can be shown that if you allow for integrating out BPS particles, but you allow ways such that the rank of the theory can be reduced, then you can construct this theory F4 with 3 flavors from 6-dimensional SCFT on a circle. So this suggests that our naive assumption that we should only allow rank preserving integrating out processes is not correct. We should allow both rank preserving and rank reducing integrating out processes, and this substantially complicates the further the integrating out procedure starting from the 60 theories. So till date, there is no surface geometry which is known that describes a 5D SCFT and does not lie in this modified classification where you allow both kind of integrating out processes. And it would be interesting to see whether one can find such a theory. Until then, it seems that all the...
I would like to ask the same question again. What exactly do you mean by integrating out BPS particles here?
It's exactly the same thing.
So is it again a limit of something?
Yes, it's again a limit on the extended Coulomb branch.
So you don't integrate out anything?
No, I'm using this as a convenience of language, this phrase.
I
So
think
it's
maybe you
integrating
could just say decoupling, which is a little bit less.
I would be happy with Sakura's language.
I think
Okay.
decoupling is also standardly used, and then there's no more confusion.
Yeah, and look, in this case, even the word integrating that does not make sense because you don't have any functional integral or anything. So you can't do any integral. So the way Sakura phrased that is perfect.
Okay. So I
It's
will
also
now...
shorter, so it's more convenient.
Okay. Yes, so now I will call it a decoupling. But in the slides, it will still be integrating out. Okay. Right. So till date, there is no surface geometry, that a known surface geometry, which describes 5D SCFT. That means it satisfies the contractibility properties, but does not lie in this modified classification. So it seems that to this date, all the known 5D SCFTs, the ones that we know, can be constructed by 60 SCFTs compactified on a circle. Okay, so now I will switch the gears a little bit and go to generalized global symmetries. Okay. So we want to study the one-form symmetry of 5D SCFTs. And it's famously known that one-form symmetries capture line defects in the theory, modulo screenings. So we want to study line defects modulo screenings in 5D SCFTs. For example, the E1 SCFT is expected to have a Z2 one-form symmetry, which means that there is a line defect which is not screened in the theory, but its square only contains screened objects. All the objects appearing in its square are screened. And this is expected from the SU2 gauge theory description. You have a fundamental Wilson line in a pure SU2 gauge theory. You have a fundamental Wilson line which is not screened, but the adjoint Wilson line is screened by gauge bosons, and the adjoint arises in the square of the tensor product of fundamental with itself. Okay, and similarly for ENF plus 1, where NF is positive, we expect that there should be no one-form symmetry, because again from the SU2 gauge theory description, the fundamental Wilson line is now screened by the fundamental hypers. But it seems that we can get a handle on one-form symmetries whenever there is a gauge theory description. But this does not tell us what happens when we have a 5D SCFT, which does not have a gauge theory description, like the E0 theory. So to study one-form symmetries for general 5D SCFTs, we need an alternate approach. And one such alternate approach is provided by surface geometries. So recall that compactifying F theory on a surface geometry constructs the external Coulomb branch, where in the IR, we have an abelian gauge theory of rank R with some massive charged matter content. So each U1I inside this U1 to the R corresponds to a compact surface in the geometry. And for each U1I, we have a Wilson line. So we have a set of Wilson lines, which is an R copies of the integer lattice. And these Wilson lines have the property that U1I charge of a Wilson line of Wj is 0, while U1I charge of Wi is 1. So this is how we are normalizing the charges. Okay. And now we want to look at what the matter content is. So matter content arises from M2 branes, wrapping various, sorry, I have written H1 over here, I should write H2. So this is an error throughout the slides. It's always an H2. So we are looking at complex curves. M2 branes wrapping complex curves, which are real two dimensions. So H2 of the Calabi-Yau threefold. And so let's pick some curve C inside this H2. Its charge under U1I is given by taking the intersection number between this curve and the surface corresponding to U1I. So this gives you the gauge charge, and this gives you a map Q from this H2 of the Calabi-Yau to this lattice of Wilson lines that we are considering, where whatever is the number, you just take that amount over here. And finally, you want to screen them, screen by all of these, this matter content. So one form symmetry, you expect the one form symmetry to be given by this lattice modulo the image of this map Q. And if you do that for 5D SCFTs which have a gauge theory description, you find that it matches what you would expect from gauge theory. And this is a general description, works for non-gauge theories as well. Right. So in this way, we can use surface geometries to compute one form symmetries of arbitrary 5D SCFTs if its surface geometry is known. Okay. Now I want to discuss another kind of generalized symmetry, which is
for being so disruptive. You presented the question as if there is a problem with theories like E0, but not for higher E's, for example.
No, there's not a problem, but you cannot, there's no gauge theory description, so you need some alternative approach, which is provided by surface geometry.
Okay, there's a challenge, not a problem. There's a challenge for E0.
This is a challenge, yes.
For E0, but not for higher E's. But you can get E0 by flowing down from higher E's. So if you have the one form symmetry at higher E, in the higher E's, and you deform by a relevant operator that takes you down to the lower E's, that relevant operator doesn't break the one form symmetry. So I don't see why you need the more complicated setup.
Well, there can be emergent one form symmetries when you flow down to E0.
Oh, but
So,
I thought no, I'm sorry. Your question was the opposite. It was not whether there are emergent ones, but whether the theory at low energies does or does not have the one form symmetry.
No,
So
it's about the conformal theory. I'm talking about the conformal theory, and the way I derive it is by looking at the low energy theory on the Coulomb branch plus BPS particles, massive BPS particles.
I find that much less convincing than flowing down from the higher E's at the origin of the Coulomb branch.
Right, but that does not lead to the full answer. So for example, in E0 case, so even has the even tilde theory does not have a one form symmetry, while E0 has a Z3 one form symmetry. So if you just slow down, you miss a lot of one form symmetries. While if you go to the extended Coulomb branch of E0, you can see this Z3 one form symmetry easily.
Sorry, what's the one form symmetry of E0?
Is Z3.
And how is it related to the Z2 of the higher E's?
It comes from even tilde theory, not even. Even tilde has no one form symmetry. So you have a theory with no one form symmetry, which flows to a theory with Z3 one form symmetry.
The regular ENs, I thought they have a Z2 one form symmetry.
No, only even has a Z2 one form symmetry. Higher E's do not have it. But even does not flow to E0.
Oh, I see what you mean. Thank you.
Can I just make a quick comment? Nani, because the converse can also happen. I mean, when you flow down, you can say that the Z2 symmetry is preserved, but it could act trivially on the fixed point in the infrared. So it could decouple. So you can't even definitively say that what you flow to has a non-trivial action of the Z2 one-form symmetry.
Okay, so let me move on to another generalized global symmetry. So here now I want to study the global form of flavor symmetry group, not just the flavor symmetry algebra. So this captures information about flavor center charges of genuine local operators in the theory, the ones which do not, which are not attached to any higher dimensional defect operators, but can just independently exist on their own. Okay, so let's fix some notation before we get there. So take some flavor, non-abelian flavor algebra, this frac F, and let capital F denote the simply connected group associated to this flavor algebra, and let Z of F be the center of this simply connected group. And now say that you have a theory where the genuine local operators in the theory are just simply uncharged under a subgroup of the center. Then the true flavor symmetric group of the theory is actually given by the curly F, which is obtained by taking capital F and modding out by this subgroup curly Z. And indeed, you can turn on flavor symmetry backgrounds in such a theory, which are principal bundles of the curly F, which are more general than principal bundles for capital F. So this is what we want to study in a 5D SCFT. We want to figure out what should be the what are the flavor center charges of genuine local operators in the theory, and if there is some subgroup of the center of the flavor of this capital F that leaves that does not act on them, and that will let us figure out what the flavor symmetric group curly F is. Okay. This can again be done from surface geometry, and it's done as follows. So flavor algebra, at least the non-abelian part of it, can be captured in some non-compact surfaces, an alpha inside the Calabi-Yau threefold. Okay, and so now we have this theory on the extended. So what we do physically is that you are at the conformal theory. Now you don't do a mass deformation because you don't want to break your flavor algebra, but just go on to the Coulomb branch of vector. Then you obtain some abelian gauge theory in the IR with some other charge matter content, which is again described by this this surface geometry in some particular singular limit. Okay, and now we conjecture that all of the property of the charges of local operators, the flavor center charges, can be computed from this this limit of the surface geometry. Okay, so you want to look at genuine local operators. So that means you want to look at things which are gauge invariant under the U1s that are arising on the Coulomb branch. So you look for that subgroup of H2 of the Calabi-Yau threefold, which does not have any charges under the various U1s. Let's call it H2 with a superscript G. Okay. In terms of the map Q discussed earlier, we want to look at the kernel of that map Q, which took us from H2 of CY3 into the lattice Z is R copies of the integer lattice. Okay. Now we want to come for this gauge invariant objects. We want to compute the charge of one of these guys in the center of the flavor symmetry of this group capital F. Okay, so take some element C inside this H2G, and you want to compute its charge. It's again given by an intersection number, which is a particular intersection number, some particular linear combination of these non-compact surfaces. And this linear combination can be figured out what it is. So using this, computing these intersection numbers tells you the flavor center charges of these gauge invariant objects. And from this, we can see if there is a subgroup inside the center which does not act on any of these, and we can compute the flavor symmetry group. So let's see for what happens for these rank 1 theories. So if you follow this procedure using the surface geometries, you find that for ENF plus 1 theories, the flavor symmetry group, the true flavor symmetry group, is always the centerless one. The center of ENF plus 1 is always modded out completely if NF is bigger than or equal to 2. So for E2, we cannot deal with the abelian part in the flavor algebra. We can only deal with the SU2 part. So if we just focus on SU2, we find that it's the global form corresponding to it is the simply connected SU2. So that at least constrains us. So it tells us that it can, the full flavor group might either be U2 or SU2 times U1, but it cannot be SO3 times U1. And for E1 theory, we can again use surface geometry to determine it precisely. And we find that it's the centerless SU2, which is an SO3 group. And all of these predictions can be checked against superconformal indices for these 5 SCFTs computed in the literature. And you find that in the superconformal index, in the expansion of it, only those representations appear which are not charged under the center for E1 and ENF plus 1, and for E2, they're charged under the Z2 center of SU2. Okay, and for the new rank 1 theory that I was mentioning, E0 adjoint, this is an SU2 flavor algebra, and now the center acts on the theory, and you find that the group should be SU2. Okay. Now I'm going to talk about 2 group symmetries of 5 SCFTs, and these are mixings of 1 form and 0 form symmetries that we discussed earlier. In terms of the properties of local operators of the theory, it captures local and extended operators of the theory. It captures information about line defects and flavor-Wilson lines together. You consider the set of line defects plus flavor-Wilson lines, and you mod it out by screenings. Earlier, when we discussed 1 form symmetry, we completely disregarded the flavor charges. And if we could just screen it, we just screen it without thinking about whether we have screened and created a flavor-Wilson line in the process or not. So let's see an example where this 2 group symmetry occurs. So it occurs in a gauge theory. So you pick a gauge theory which has spin 4n plus 2 gauge group, and take 8 supercharges and take some fundamental hypers, NF number of fundamental hypers. The 1 form symmetry for this gauge theory is Z2, because there is a spinor-Wilson line. Its square has the fundamental Wilson line in it, the vector Wilson line, and that is screened because you have hypers. Okay. The flavor algebra is SP and F, and the corresponding flavor group, the simply connected one SP. And now the hypers that we use for screening are actually in bifundamental of spin times SP. So when we looked at the screening, we were a little bit hasty. We should have said that S squared is fundamental of the spin gauge group, but that by screening is actually not trivial, but actually equal to fundamental of this fundamental Wilson line for this SP and F. So the square is not trivial if you keep account for flavor charges. Only the 4th power of it is trivial, because the 4th power is equivalent to adjoint that is screened by gauge bosons, which do not carry flavor charges. So the full group of line defects plus flavor Wilson lines modulo screenings is actually a Z4, which we denote by E. So this is a theory, this is a Lagrangian gauge theory, in which the 1 form symmetry Z2 is somehow enhanced to a Z4 structure if you care about the flavor part of flavor symmetry. And this is a sign of 2 group symmetry. Indeed, there is a non-trivial 2 group symmetry in this theory. So in general, in a general theory, what can happen is as follows. You have a 1 form symmetry, which enhances to some, if you consider flavor Wilson lines as well, it enhances to some group E, inside which sits some flavor Wilson lines Z that we were modding out to compute the global form of the zero form flavor symmetry. And so they form a short exact sequence, these groups. And the condition for a non-trivial two-group symmetry is that the sequence should not split. If the sequence splits, there is no non-trivial two-group symmetry. But if it does not split, then you have a non-trivial mixing between one form and zero form. Okay. And now in the context of 5D SCFTs, these two-group symmetries can be also computed from surface geometry. It's all encoded in the intersection data. Okay. So what is the set of line defects? Our strategy is again the same. We do not perform a mass deformation, but we go into the Coulomb branch of VACO, of the conformal theory. And then from the point of view of the IR abelian theory, the line defects plus Flavor-Wilson lines form this lattice. The line defects for forming are copies of the integer lattice, and the Flavor-Wilson lines are forming this center of the flavor symmetry group of this capital F associated to flavor algebra. Okay, and now we want to compute the gauge and flavor charges, flavor center charges of various curves, which correspond to the various matter content in this case theory. Okay, so we compute both flavor and center charges. This gives us a map Q from H2 of the Calabi-Yau threefold into this lattice. And then the set of equivalence classes we are looking for, modulo screenings, is given by taking this lattice and modding it out by the image of this map Q. And from this, we can extend it, we can supplement it with the definition for the one form symmetry group discussed earlier. And we can find of the full short exact sequence as well. Okay. And if this short exact sequence does not split, we say that the 5D SCFT has a non-trivial two-group symmetry. So an example is provided by the simple even theory. As we discussed earlier, it has a Z2 one-form symmetry. The Z participating in the short exact sequence is Z2 because the flavor symmetry, the global form of the flavor symmetry group was SO3, which is SU2 mod Z2. So this Z2 appears over here. And if you compute this equivalence classes of line defects plus Flavor-Wilson lines, line defects plus Flavor-Wilson lines modulo the screenings, the question is it Z2 times Z2 or Z4? And we find that this is actually a Z4. So the short exact sequence formed by these three groups OZ and E is a sequence which does not split. And so the even theory should have a non-trivial two-group symmetry. Okay, and now using surface geometries, you can compute two groups for arbitrary 5D SCFTs as well. There are two kinds of two groups which arise in general. There are these kind of instantonic ones which are not visible from gauge theory, as for the even theory, and sometimes like the spin 4n plus 2 plus flavor ones, which are visible in the gauge theory and are also in the conformal theory. So the gauge theory answer is modified a little bit by the instantonic corrections. Okay. So that brings me to the end of my talk. I hope I have given an overview of how surface geometries have led to progress in understanding the classification of 5D SCFTs and progress in understanding generalized global symmetries of 5D SCFTs. And there are some future interesting directions which can be pursued. So first of all, these surface geometries do not actually give us a handle on the geometry relevant for the conformal theory. For example, if you want to compute the Higgs branch of the 5D SCFT. And what would be more useful in that situation would be to have an algebraic construction of the Calabi-Yau singularity describing the conformal point as some intersections of hypersurfaces inside some ambient space. And such a correspondence between surface geometries and the algebraic models is not known at this moment. So it's not, both of these directions need to be understood. How to go from algebraic model to surface geometry. This is pretty much understood. You simply resolve the Calabi-O3 singularity. It's the other direction which is less well understood. Okay. Then another interesting direction is to study if there can be rank 0 5D SCFTs. So in this surface geometries, we always started with some collection of surfaces. So we always had some non-trivial rank. If you had no surface, there was no surface geometry. So it's not sensitive to exploring rank 0 5D SCFTs. And some work in this direction has recently been done, trying to study this kind of algebraic models of Calabi-O3 singularities. But it's not clear at this moment whether they are discrete gaugings of free hypers or not. If we can find some models which are, and we can definitively prove that they are not discrete gaugings of free hypers, they would be very interesting rank 0 5D SCFTs. That will be new SCFTs. Okay. Another interesting direction is to understand what this new rank 1 5D SCFT I talked about, learn more about it. For example, how to compute a superconformal index, and to understand in the M theory construction what is the non-geometric ingredient that is involved. When we come to generalized symmetries, we went on to the Coulomb branch of Vector of the conformal theory to get a handle on these two group symmetries. So we essentially computed it from low-lying data on the Coulomb branch. So we understand how the two group symmetry of the conformal theory manifests on the Coulomb branch of Vector, but currently it's not completely understood how it manifests on the Higgs branch of Vector. So that would be an interesting direction to explore. And finally, I didn't talk about the 't Hooft anomalies of these one-form symmetries and two-group symmetries at all. And that would be a very interesting direction, as they would have some nice interplay with the group structure of two-group symmetries itself. So thank you for your attention.
Okay. Thank you very much, Lakshya, for a very nice talk. So are there any questions? So let me ask one. So you have this classification program. How would you find, or do you think it is a complete classification program, or is there a possibility that you are missing something?
Right. So as I said, no surface, as far as surface geometries are concerned, we don't know an example which would satisfy contractibility conditions and which does not arise in this list from 60 SCFTs. So, and of course, we have not explored all examples, but it's just that whatever infinite classes of examples we have explored, they all seem to come from 60 SCFTs. Now, this rank 0 5D SCFTs are, I think, an interesting way in which we can construct new theories that are not in the previous class, because there you will definitely have more than rank 0. Right.
And these rank 0 5D SCFTs, if you compactify them to 4D, would give a rank 0 n equal 2 for the SCFTs? Or,
yeah,
I mean, if they are not the discrete gauging of free hypers, would you expect them also not to be discrete gauging of free hypers in 4D?
I don't know how to argue that.
Okay. Okay.
But yeah, it would be interesting because of that reason. You can, in 4 dimensions, if there exists such 5-dimensional theories, you can hope that in 4 dimensions there would also exist, and try to understand them by circle compactifications of these 5D theories.
Okay. Are there any more questions? Okay. If there are no more questions, let's thank Lakshya again. And we will switch off the recording, and so people